Hello everyone. Welcome to this video on learning mathematics through concept and examples. Today we are going to look at some example problems on derivative. Let's begin with this one here. Example, find the derivative of the function y equal to cosine x using definition. So in this problem, we are asked to find the derivative using definition. So we need to know the definition to find the derivative. So when I say definition, it is the limit definition of derivative, which is like this. The derivative of the function y with respect to x, dy over dx is equal to the limit as h approaches to 0 of f of x plus h minus f of x divided by h. That is the definition. So here our function is y equal to cosine x. So we are going to plug in the values over there and find the derivative. Now the derivative dy over dx is equal to limit as h approaches to 0. So f of x or y is cosine x. So f of x plus h will be cosine x plus h. Then minus f of x, which is cosine x divided by h. This will be equal to limit as h approaches to 0. Cosine x plus h, we are going to use the formula for cosine a plus b. So it will be cosine x times cosine h, then minus sine x times sine h. At the end, we have minus cosine x, all divided by h. You know, we cannot find this limit directly by direct substitution because denominator will be 0. So we have to simplify a little bit to make it valid without direct substitution. Now in the numerator, from the first and the third term, I'm going to factor out cosine x. So limit as h approaches to 0, cosine x common in the first and the third term. So we get cosine h minus 1. And then minus we have sine x, sine h, sine x times sine h. And this denominator is for everything. Now I'm going to separate the denominator. So we can separate the denominator like this. Now we have two terms here. This is the first term. This is the second term. So we can find the limit of each term. So this is equal to limit as h approaches to 0, cosine x times cosine h minus 1 over h, then minus limit as h approaches to 0, sine x times sine h divided by h. Now you can see h is changing here, h approaches to 0. So for this limit, this one, cosine x is constant. So you can pull that out. And we get limit as h approaches to 0, cosine h minus 1 over h. And then minus in the second limit, similarly, sine x is a constant. You can pull it out. We'll have limit as h approaches to 0 of sine h over h. Okay, now we have few more steps to get the final result. We have cosine x here multiplied 2. Now limit as h approaches to 0 of cosine h minus 1 over h is a 0. So that is the limit of this function, that is 0. That's a formula. Minus sine x multiplied 2. Limit as h approaches to 0, sine h over h. That is also a formula, which is 1. So that limit is also 1. So we get this equal to, so this is a 0. 0 times cosine x 0. 0 minus sine x times 1 is a negative sine x. Negative sine x. So meaning of that is the derivative of the cosine function, okay, derivative of cosine x with respect to x is negative sine x. Okay, let's move on to next one. Example, find dy over dx or derivative of this function here. So let's write that function. Y is equal to 2x squared plus 1 over x minus 1. So here the function is given in the form of quotient. So we'll use the quotient rule. So quotient rule is the derivative of y with respect to x is equal to denominator x minus 1 times the derivative of the numerator, derivative of 2x squared plus 1, minus numerator, that is 2x squared plus 1, times the derivative with respect to x of denominator, everything divided by the square of the denominator. So we use the quotient rule. That is the quotient rule. Now this is equal to x minus 1. Derivative of 2x squared plus 1 is a 4x. Then minus 2x squared plus 1. The derivative of x minus 1 is a 1. Divided by x minus 1 quantity squared. Now, if we simplify this further, in the numerator, we can distribute this 4x. 4x times x is a 4x squared. And then 4x multiplied to negative 1, that's minus 4x. And then here we are multiplying by 1, so it is 2x squared plus 1, but we are changing the sign because we are multiplying by negative in front. So that is negative 2x squared minus 1. Divided by, in the denominator, we have x minus 1 quantity squared. So far, what we have done is we use the quotient rule and we are just simplifying it. So let's simplify a little further. If we look at the numerator, here we have a 4x squared minus 2x squared, that is 2x squared. And we have minus 4x minus 1 over x minus 1 squared. So that is the derivative of that function. The function is given in the form of algebraic fraction, or it is a rational function. Because this function is a rational function, we use the quotient rule. So here we use quotient rule. So if you see the function, or if you see the rational function, you can use quotient rule. Or if you see the function in the form of numerator over denominator, you can use the quotient rule. Okay, next one here. We have to find the derivative with respect to x of this function. So first, our function is y equal to square root of 2x squared plus x minus 3. So this is a square root function. So if you remember the derivative of a square root function, derivative with respect to x of square root of x is 1 over 2 square root of x. That is when the quantity inside the square root is just x. But here you can see inside the square root, we have a quadratic function. So in fact, this function is the composite function. Okay, this function is composite function. So we are going to use chain rule. So we can write like this. Derivative of the function y with respect to x is equal to, according to chain rule, we find the derivative of outside function and multiply by the derivative of inside function. Derivative of the square root function is 1 over 2 times the square root of whatever is there inside the square root. Then multiply by the derivative with respect to x of the inside function. That's our inside function. So now if we try to simplify this, let's see what we get. 1 over 2 times the square root of 2x squared plus x minus 3. Derivative of 2x squared is 4x. Plus derivative of x is 1. And the derivative of 3 is a 0. So we get 4x plus 1. Now, if we simplify this, 4x plus 1 multiplied with 1 is 4x plus 1. And in the denominator, we have 2 times the square root of 2x squared plus x minus 3. So that is the derivative of this function, y equal to square root of 2x squared plus x minus 3. So in this one, what we did is the function given was composite function. Okay, that was the composite function. Because it was composite function, we use the chain rule. We use the chain rule. If you remember in the previous example, the function given was a rational function. Okay, function given was a rational function. So we use the quotient rule. But in this one, the function given was composite function. So we use chain rule. Okay, let's move on. Here is the next example. We have to find a dy over dx. That is the derivative for the function cotangent x times y equal to x minus y. So you can clearly see this function is implicit function. This is implicit function. Implicit function. So if it is implicit function, we use the implicit differentiation. That is, we have to differentiate on both sides with respect to x. So that's where we start. So let's do that. Differentiating both sides with respect to x, what we get is on the left, the derivative of cotangent xy. You can see we have a cotangent function. Inside function is xy. That is a composite function. Okay. Cotangent xy is a composite function. So we use the chain rule. Chain rule says derivative of outside function. Derivative of cotangent is negative cosecant squared xy. Then multiply by the derivative with respect to x of the inside function xy, equal to, on the other side, derivative of x with respect to x is 1, minus derivative of y with respect to x. We just write dy over dx. We want to find the value of dy over dx by solving this equation. Now, on the left, we have cosecant squared xy multiplied with the derivative of x times y. So this is a product rule. So because we have the derivative of x times y, multiplication, two functions are in the form of multiplication. So we use the product rule. Product rule says first function x multiplied with the derivative of second dy over dx plus second function y times the derivative of first function is 1 equal to 1 minus dy over dx. Now, in order to find dy over dx, we need to simplify the left-hand side by distributing this cosecant squared xy, negative cosecant squared xy, to these two terms here. So if I multiply with the first, it will be negative x times cosecant squared xy dy over dx. So I can write negative x times cosecant squared xy multiplied to dy over dx. Then plus and minus, this is plus and multiplied with minus, that will be minus y times that quantity. So y times cosecant squared xy equal to 1 minus dy over dx. We need dy over dx. So I need to move this term on the left-hand side because it has dy over dx. Also, this one has dy over dx. So I'm going to keep that term on the left-hand side. This term does not have dy over dx. So I'm going to move it to the other side. So if I move this to the left-hand side, it will be positive. So I can write dy over dx. And then here we have minus x times cosecant squared xy dy over dx equal to 1. And then if I move this one to the other side, it will be plus y cosecant squared xy. So we are trying to find dy over dx. That's why we bring all dy over dx on the left-hand side, and we simplify for that. Now let's simplify further. On the left-hand side, what we can do is we can factor out this dy over dx. So if we factor out dy over dx, we'll have 1 minus x times cosecant squared xy. On the other side, we have 1 plus y times cosecant squared xy. So we are almost there. We want to find dy over dx, but here dy over dx is multiplied with this. That means we have to divide on both sides by this quantity to find the value of dy over dx. So what we'll do is we'll divide on both sides by 1 minus x cosecant squared xy. 1 minus x times cosecant squared xy. So on the left-hand side, that quantity get canceled, and we'll just have dy over dx. So finally, we'll have the derivative of the function y with respect to x equal to 1 plus y cosecant squared xy divided by 1 minus x cosecant squared xy. So that is the derivative, okay? That is the derivative of this implicit function given here. So the key here is, if the implicit function is given, we have to use the implicit differentiation. And when you are performing the implicit differentiation, you may say different rules. Here, we use the derivative of the trig function, derivative of cotangent is negative cosecant squared. Also, we use the product rule here because we have the derivative with respect to x of x times y. So we use the product rule. So, but the first step is to start with the implicit differentiation. And then once you use all rules and find the derivative, what you have to do is your equation will have dy over dx. You have to bring all dy over dx on the left-hand side and solve for that dy over dx. So that's how we can find the derivative of implicit function. Next one here is the derivative of the inverse tangent function. Find dy over dx for y equal to inverse tangent function, the square root of 1 plus x over 1 minus x. Okay, now let's try to recall a couple of formulas here. Derivative with respect to x of tangent inverse x is 1 over 1 plus x squared. Okay, reciprocal of 1 plus x squared. Similarly, if you remember the derivative with respect to x of square root of x, it is 1 over 2 square root of x, or you can also write it like this. This is same as 1 over 2 times 1 over square root of x. So we'll be using these two formulas here to find the derivative. So our original function is y equal to tangent inverse. You can see your outermost function is the inverse tangent function. Then next to that, we have the square root function. And inside that, we have 1 plus x over 1 minus x. That is the rational function. So we have to use the chain rule here. First, we have to find the derivative of this tangent inverse, then the derivative of a square root function, and then the derivative of innermost function using the quotient rule. The inside one is in the form of a fraction, so quotient rule there. So let me write that. So it's going to be a little bit longer here. So dy over dx is equal to derivative of tangent inverse is 1 over 1 plus x squared. In place of x, see, if we have tangent inverse x, we have this one in place of x. So when we square that, it will be 1 plus x over 1 minus x. then multiply by, now we go to the next. We have to find the derivative of this square root function. Derivative of a square root function is 1 over 2, then times 1 over square root of x. 1 over means the reciprocal and then square root of x. So reciprocal of this one, reciprocal of 1 plus x over 1 minus x will be 1 minus x over 1 plus x with the square root. And then multiply by the derivative of the innermost function, derivative with respect to x of 1 plus x over 1 minus x. So what we did here is we used the chain rule because this was the composite function. Okay, the function given was composite function. Because that was composite function, we use the chain rule. So in this step, we use the chain rule. So always remember, if the function is given in the form of a composite function, then we have to use the chain rule. Now we need to simplify that. Let's see what we get by simplifying. So this implies the derivative, which is dy over dx. On the left side, we write dy over dx equal to, now in order to simplify this fraction, we multiply both numerator and denominator by 1 minus x. So if I multiply the numerator by 1 minus x, that will be 1 minus x. And in the denominator, if I multiply by 1 minus x cancel here. Here you'll have 1 minus x. 1 minus x plus 1 plus x, that is a 2. Multiplied with half times the square root of, okay, let me write it like this. 1 minus x is square root of 1 minus x in the numerator and is square root of 1 plus x in the denominator, because that is square root is for both. So we can write like that. Then multiply by, we have to use the quotient rule here. While using the quotient rule, we say denominator, which is 1 minus x, multiplied with the derivative of numerator, which is 1, minus numerator, 1 plus x, times the derivative of denominator, which is negative 1, divided by the square of the denominator. So that will be 1 minus x quantity squared. Okay, let's simplify further. Derivative of the function y with respect to x equal to, okay, here we have 1 minus x times 1 minus x. If I go up to here, okay, so this is 1 minus x raised to half, and this is 1 minus x raised to 1. So that will be 1 minus x raised to 3 over 2. 1 minus x raised to 3 over 2. And in the denominator, I have 2 times 2, that's a 4. And then the square root of 1 plus x. Now over here, you can see this is 1 minus x. And when we distribute this negative, and negative is positive, so that is 1 plus x. So 1 minus x plus 1 plus x is a 2. So if we simplify the numerator, that is a 2. 2 divided by 1 minus x squared. I mean 1 minus x quantity squared. Okay, few more steps now. So this implies dy over dx, derivative of the function y with respect to x equal to, okay, let's see. So when we look at this one, these 2 and 4, okay, 2 and 4, if you divide, that will be half. 2 divided by 4 is half. And then we have 1 minus x raised to 3 over 2. That is 1 minus x raised to 1.5. 3 over 2 is 1.5. And here is 2. So if we simplify that, it will be 1 over x 1 minus x raised to half, or square root of 1 minus x. And then this one will still remain in the denominator. So 1 over the square root of 1 plus x. So if we try to simplify this to get the final answer, our final answer will be derivative of the function y with respect to x equal to, in the numerator, 1 times 1 times 1, that's a 1. In the denominator, we have 2. Both functions have a square root. They are in multiplication, so we can put single square root there. And then we have 1 minus x times 1 plus x. This is like a minus b times a plus b, which is a squared. 1 squared is 1 minus b squared, that is x squared. So the derivative of this tangent inverse or inverse tangent function that is given here is equal to 1 over 2 times the square root of 1 minus x squared. So in this problem, what we did is, because the function was composite function, composition of 3 different functions, in fact, okay, we use the chain rule. We first write the derivative of the outer function, tangent inverse function, then the derivative of this square root function here, and finally the derivative of innermost function, which we evaluated here using the quotient rule. So we are using chain rule, but we have 3 steps for using the chain rule. And the main function was inverse trig function there. Okay, next one now. Find dy over dx, or derivative of this function y equal to x raised to x. You can see the base of the function is a variable and power is also variable. So we don't have formula for that. If we have something like this, if we have derivative with respect to x of x to the n, x is variable, but n is constant, then we have the power rule, which is n times x to the n minus 1. But we cannot use that here because in place of n, also we have the variable. We have another formula, derivative with respect to x of b to the x. See, b is a constant and x is the variable. X variable as it is, but b is constant. In that case, the formula was b to the x natural log b. This was the exponent rule. This was the power rule. Okay, the first one, the first formula, that is a power rule. And this one is the derivative of exponent or exponent formula. You can say derivative of exponent. Or exponential function. So both formulas cannot be used here. If that is the case, what you have to do is we have to take natural log on both sides. So you can see here we have the function y equal to x to the x. If you take natural log on both sides, it will be natural log y equal to, when you take the log, exponent will come in front. So it becomes x times natural log x. And after that, we can differentiate on both sides with respect to x, just like in implicit differentiation. Differentiating both sides with respect to x. So what do we get? So here we have the composite function. Your outside function is natural log function, and inside function is y, which in fact is a function of x. So what we do is we find the derivative of outside function. Derivative of natural log function is 1 over the argument, that is 1 over y, and then multiply by the derivative of inside function, dy over dx, equal to, on the right side, we have 2 functions in the form of product, so we can use the product rule. Product rule says first function x multiplied to the derivative of second function is 1 over x, plus second function, natural log x, multiplied with the derivative of first is 1. So what I'm getting is 1 over y times dy over dx is equal to x times 1 over x, that's a 1, plus 1 times natural log x is natural log x. We want dy over dx, so to get rid of this y, we multiply on both sides by y. So we multiply the left-hand side by y, and also we multiply the right-hand side by y. So if we do that, our derivative will be y and y cancel on the left-hand side. We get dy over dx, the derivative of the function y with respect to x equal to y. Y is x to the x. So I can write x raised to x and then 1 plus natural log x. So that is the derivative of the function. So derivative of the function y equal to x to the x is the same function multiplied with 1 plus natural log x. So here both base and exponent are variable. So if both base and exponent are variable, the best way to find the derivative is by taking natural log on both sides. So this is the derivative of the exponent, which has both exponent and also the base in the form of variables. Here's the next example. We have to find the derivative with respect to x for the function y equal to 5 over 1 plus 3 to the x. So let me write the function first. Y equal to 5 over 1 plus 3 to the x. So we can clearly see this is not exactly a rational function. We don't have variable in the numerator, but we just have variable in the denominator. So we can rewrite this function as y equal to 5 times 1 plus 3 to the x raised to -1. Because if I move this to the numerator, it will be the reciprocal or power -1. Now, in order to find the derivative, 5 is a constant. For the power, we use the power rule. And for the inside function, because this is a composite function, for the inside function, you can see there is an exponent. So we have to use the exponent rule. So that is this one. Derivative with respect to x of b to the x is equal to b to the x multiplied to log b. That's our formula. So what we can do is, if we want to find the derivative, so the derivative will be dy over dx is equal to 5 is a constant, we can keep there. But this one, this function 1 plus 3 to the x raised to -1, that function is composite function. Okay, that is composite function. Meaning of that is we have to use the chain rule. So first we have to find the derivative of outside function. Outside function is a power, so we use the power rule. That means we bring that power down and decrease the power by 1. If you decrease the power by 1, that will be -2. -1 minus 1, that will be -2. And multiply by the derivative of inside function. Multiply by the derivative with respect to x of the inside function, 1 plus 3 to the x. So what we use here is chain rule. Okay, what we use here is chain rule. That is chain rule. Now let's simplify. So dy over dx, the derivative of the function y with respect to x, equal to, first, 5 times -1 is a -5. And then here we have 1 plus 3 to the x raised to -2. If I want to write as a fraction, then it will be 1 plus 3 to the x raised to +2. Then let's multiply by the derivative of this one. Derivative with respect to x of 1 is a 0. So I don't have to write for that. But this one, derivative with respect to x of 3 to the x is just like this. It's like b to the x. B to the x will be b to the x natural log b. So this will be 3 to the x natural log 3. 3 to the x natural log 3. So my final answer will be derivative with respect to derivative of the function y with respect to x is equal to, okay, let's multiply constant with constant. So that will be -5 natural log 3. And the variable we have here is 3 to the x divided by, in the denominator, 1 plus 3 to the x quantity squared. So that is the derivative of this exponential function given here in the form of a fraction. Okay, so that's how we can find the derivative when function involves the exponential function. We use the derivative of the exponential function, which is here. Okay, up to here, we work on several examples on how to find the derivative of the function. Now we are going to look at two applications of a derivative. The first one involving the rate of change. Okay, here is our question. The altitude of triangle is increasing at the rate of 2 centimeters per minute, while the area of the triangle is increasing at a rate of 4 centimeters squared per minute. At what rate is the base of the triangle changing when the altitude is 10 centimeters and area is 80 centimeters squared? Okay, here we are talking about a triangle. So let's first draw a triangle. So let's draw a triangle. Okay, that's my triangle. Let me name it as triangle ABC. This is the base of the triangle B. And this one is the altitude of the triangle H. Now let's see what is given. The altitude of the triangle is increasing at the rate of 2 centimeters per minute. So here, altitude of the triangle, that is change in height with respect to time, dH over dt is equal to 2 centimeters per minute. That is given. Well, the area is increasing at the rate of 4 centimeters square per minute. Area, that is dA, change in area with respect to time, is equal to 4 centimeters squared per minute. So here we are looking at the, or I should say the change in height with respect to time is given. So this is increasing. So because the height is increasing, area is also increasing. Now what you have to do is, at what rate is the base of the triangle changing? So when the height is increasing and also area is increasing, maybe the base of the triangle is also increasing. Maybe the base is increasing or maybe it is decreasing. So changing, right? At what rate is the base of the triangle changing? And we have to find that when altitude is 10 centimeter and area is 80 centimeter. So let's see what happened when we have those two pieces of information given. Okay, so when altitude or height equal to 10 centimeter and area equal to 80 centimeters squared, let's see what happened. So what we know is, we know the formula for area. We know area of the triangle is half base times height. So here in this condition, they have given the height or altitude and area. They have given the altitude and area. Base is not given. So we can find the base. So if we rearrange that, base will be equal to 2 times area divided by h. Base is equal to 2 times area is 80 divided by h is 10. So that means our base is equal to 16 centimeter. So during this time, when the base is 16 centimeter, height is 10 centimeter, and area is 80 centimeter, if these two changes are occurring, at what rate is the base changing? That's what we need to find. So let's work on that calculus part now. We have the same formula. We have area equal to half base times height. Okay, area equal to half base times height. Now let's differentiate this one on both sides with respect to time. Differentiating both sides with respect to time. If we do that, on the left hand side, it will be derivative of area with respect to time equal to half on the other side is a constant. And to find the derivative here, we use the product rule. First function b times the derivative of second dh over dt plus second function h times the derivative of first is db over dt. So dA over dt, now let's plug in the values. dA over dt is 4 equal to half multiplied to base of the triangle. B is 16 multiplied to dH over dt. You can see dH over dt is a 2 plus 10 times dV over dt. We want to find that. So now let's see what we get. If I distribute this half here, half of 16 is 8. So 8 times 2, 16. Plus, if I distribute this half here, half of 10 is a 5 multiplied to dV over dt. So if we solve this, dB over dt is equal to, okay, if I subtract 16 on both sides, it will be negative 12. And when you divide that negative 12 by 5, it will be negative 2.4. Negative 2.4 centimeter per minute. Meaning of that is base is decreasing at this rate. Okay, so meaning of that is base of triangle is decreasing. Base of triangle is decreasing at 2.4 centimeter per minute. Meaning of that negative sign is decreasing. Base is decreasing at that rate. So in this example, we see application of derivative involving rate measure. Now in the last example, we are going to look at application of derivative to find the equation of tangent line. So here is the example. Find an equation of line tangent to the graph of the function y equal to square root of x at x equal to 4. Let's see. So they have given the function. They have given the function y equal to square root of x. In order to find the equation of the tangent line, we need the point at which we are drawing the tangent. And also we need the slope. First, let's find the point. Point of tangency will be, we are finding the equation of the line at x equal to 4. So x coordinate is 4. And you can see when x is 4, if you plug in x equal to 4 here, when x is equal to 4, your y will be equal to square root of 4, that is equal to 2. So the point of tangency is 4, 2. That is the point. Now we need the slope. To find the slope, we have to find the derivative at x equal to 4. So let's find the derivative. Now the derivative of the function dy over dx is equal to derivative of the square root function is 1 over 2 square root of x. So this implies the slope m is equal to, we are finding the slope at x equal to 4. So we have to plug in 4 into this equation. So this will be 1 over 2 times the square root of 4, which is 1 over 2 times 2, which is 1/4. So the slope is 1/4. So once we know the slope and the point, we can easily find the equation of the tangent line. So let's write the equation of tangent line. Equation of tangent line is y equal to m times x minus x1 plus y1. So here I'm writing the equation of the tangent line in point slope form. This form of equation is called point slope form, because we have the slope here and we have the point. This point here is the point x1, y1. This is the point x1, y1. Now we can plug in x1, y1 and the slope m into this equation to get the equation of the tangent line. So let's do that. y equal to slope m. You can see it is 1/4 here. Then we have x minus x1. x1 is 4. Then plus y1. y1 is 2. So what I'm getting is y equal to 1/4 multiplied to x is 1/4 x, and then minus 1/4 multiplied to -4 is -4 times 1/4, which is -1. And then we have a plus 2. So final equation will be y equal to 1/4 x plus 1. So that is the equation of the tangent line. And you can clearly see the equation is in the form y equal to mx plus b, where the slope is 1/4 as we get here, and the y-intercept is 1. So that is the next example of the derivative of the function. So we look at two applications of derivative. One about the rate, or related rate we should say, and this one finding the equation of the tangent line. So that's all for this video. Thank you for watching. I hope this is helpful.